Welcome. Last lecture today. Tomorrow is Easter. Don't forget to hunt for eggs. That's important. Next week, the lectures will be cancelled, just as a reminder. No reason to show up. And the week after, we will do the presentations starting on Tuesday with 8 of the presentations and the Thursday, the other 8 presentations. I really hope that everybody will show up, and I will try to enforce attendance for these 2 lectures so that we have a crowd to speak to, which might be better than sitting in front of an empty audience. Okay, so as announced already, what I wanted to do today is to talk about a topic that might not be directly related to using C++ in scientific applications or parallel C++, but it's still very important because of the widely used Python programming language, which is gaining momentum left and right, and the whole community is being used in many fields and slowly creeps into scientific computing as well. They're mostly as a visualization tool, so that you generate data with your application, and then you use Python to visualize that data in a very convenient way with matplotlib or Pandas or other libraries that are kind of well established. So what I'm interested in today is to talk about how can we actually combine C++ with Python, which sounds a bit strange because when you look at Python, it's a language which is weakly typed or dynamically typed. So only at runtime types are being checked to a certain extent. It's scripted. It's very rapid development cycle. You can do that interactively in that rapid environment. You have very nice integration into Jupyter notebooks, so you have a visual way to work with Python. So there are many tools that make Python very interesting for these very rapid development cycles. On the other end, you have C++, which is a very strongly typed language, a compiled language, and on first glance, it seems that these 2 languages don't fit together. But as it turns out, C++ and Python are perfect brethren. They fit together very, very well. Because on the one hand, you can combine the user-friendliness, the vast library infrastructure that Python gives you with the excellent performance C++ can provide you with. Actually, when you look at Python and the Python libraries and the existing Python libraries, many of those libraries are actually written in C or C++. Just take NumPy, for instance. NumPy is just written in C with a very thin Python wrapper around it. Other libraries go a slightly different way. Pandas, for instance, is halfway written in Python itself, and only part of it is written in C++ or in C. So you see that these 2 languages taken together give you the best of both worlds. They give you performance on one hand and user-friendliness on the other hand. So just imagine you have very complicated data analysis to do, and Python itself is not fast enough. So you're kind of stuck with that because you have to wait for too long. So you want to take part of your Python application that you already have written, and you identify that there's 1 or 2 types in that Python application that are actually the culprit, because they slow you down. Wouldn't it be nice if you could just take out these 2 Python types and replace them with equivalent C++ code, which gives you a factor of 10 performance gain? And I want to guide you today through a very, very simple type to do that with you. And then I will talk about various facilities of how you can bind certain features of C++ to Python, how you can call Python functions from the C++ side if you want, or vice versa, where you can actually take full Python code and on the C++ side and call eval on the Python side and things like that. So there's a very close integration of these 2 things available to us. So it's very, very important. And I had to do it many times in my career, and I'm very happy that I actually learned how to do that. Okay, so how do you do that? How do you combine Python with C++? Well, as I said, Python is written in C itself, and it exposes a vast C API you can use to write code. And people have written a lot of Python modules in C, but quickly realized that this is not the most pleasant of exercises. Just based on the, you might know that, I don't know if you have ever worked with a Python API, with a C side of the Python API. All Python objects, everything in Python is a reference counted object. Reference counted object means that you have a pointer to it, and whenever you copy the pointer in your C code, you have to call a special Python function which increments the reference count on that object. And whenever that pointer is not needed anymore, you have to call another function which decrements the reference count on that object, which leads to the possibility to dynamically delete things when the last reference count goes out of scope, when you decrement your reference count to 0. Now you can imagine that this is kind of a pain, because it's so easy to forget a address or a release just when you're copying pointers around to another function. And if you forget to increase the reference count, you probably will run into segmentation faults, because suddenly somebody releases a pointer you are still holding onto. On the other hand, if you forget to do a decrement of a reference count, you will run into memory leaks. So things will never be freed, because things in Python are always deleted only when the reference count of that object goes to 0. So people have started to think, how can we automate that? C doesn't allow us to automate that. So people have started creating tools that actually help binding existing code to the Python side of things, so I don't have to write the whole wrapper in C++. One of the first tools that came up is Swig, SWIG, a generator tool that generates bindings between languages. So it's not Python or C++ or C related. It can generate all kind of bindings between all kind of languages. But it's used for Python as well, especially when you have more languages in a project, not just C and Python or Fortran or other things, then Swig is quite useful. But it doesn't generate Pythonic code. So the interfaces generated by Swig is not really what you would expect from the Python side. You give it a C header with your declarations of the functions, and Swig will generate the Python code that makes it available, these functions available in Python. So this is not the perfect thing to do. But if you want to look at it, it's an interesting tool developed a long time ago, essentially, I think in the 80s, even before the internet, that started to be developed. Another tool is Cython. Cython is a compiler that takes Python code and some extensions to Python code and generates C code from it. So it translates Python to C. So you can essentially sketch your code in Python, take Cython and generate the C code from it. Sounds compelling, but there are many disadvantages, and I will show you in a second what the main disadvantage is. It's impossible to read that code that is being generated, and you can't debug that. So it's incredibly difficult. I'll show you an example in a minute. Then there are C types, that standard module that comes with each Python installation, where you can, on the Python side, say, hey, I want to call a C function that takes an integer, a double, and will return me a string. And that C types will generate the bindings, and then you can somehow connect that to your C function. Again, limited to C only. So it's not really good at C++, and we want to look at C++. Boost Python is the first step in the right direction, early 2000s. It was developed back then in the context of the Boost project. This is a C++ library that actually binds C++ code to Python. And while it's nowadays a bit outdated in terms of features, in terms of style, how it's being coded, it has lent or has defined the standard of the API, how C++ how you have to write your code in order to expose C++ to Python. So in that sense, it's very important, and you can read about it. It has an extensive documentation. A very interesting project. Impossible code to read on the C++ side, by the way. So that's one of the disadvantages. But what I want to focus on today is PyBind 11. It's a very lightweight C++ library, about 8,000 lines of code, that exposes a very similar interface to Boost Python, because people have realized what Boost Python has created is very useful. It's very productive. So people use that interface still, but it's implemented in a more modern way, in a more lightweight way, just learned from the mistakes of Boost Python. There is a newer version of PyBind 11, which is called NanoBind. It's a completely different library. Well, people said, okay, PyBind 11 was developed for C++ 11 in, well, 10 years ago, 12 years ago. Why not have a library that is more modern in terms of C++, even smaller, even more lightweight? But again, exposes a very, very similar interface to PyBind 11. So I want to focus on PyBind 11 today because it still has the broadest, the most complete bindings. But once you understand how PyBind 11 works, you can work with NanoBind in the same way you can work with Boost Python. So there's not much difference. So let's focus on PyBind 11. But first, how do we expose C code or C++ code to Python? Well, if you're a Python developer, you know that each Python file is essentially a module in Python. And you can import that module into another module and then use the functionalities that are there. The Python extension modules follow the same scheme. They say, okay, if you create an extension module in Python, you create a shared library, and that shared library looks like as if it was a Python module that is written in Python itself. It's just not written in Python, it's most likely written in C++. So why do you want to do that? Well, you want to possibly interface with existing libraries. You have some C library, some C++ library that is there, you don't want to rewrite it, you want to just make it available in Python. You could replace performance critical code that you have in your Python program, just isolate that, replace it with a new module. You can first prototype your application, your library or your solution in Python until you're happy with the interface. And then you say, okay, I have the interface, now I write it in C++. You could run tests for non-Python libraries in Python easily, just as another example. So as I said, Python itself is written in C and has a vast API for writing C modules for Python. And half of the Python infrastructure is written using that, well, all of it is written using that API. Even PyBind 11 relies on that API. But half of the modules that are being installed when you install Python have been written in native C using that API directly. I don't envy those people who have used that and have done that. I admire them because they are able to use that C code and make it bug-free, which I don't want to do. It's really very, very painful. Because you have to do manual reference counting, as I said. Whenever you copy a pointer to a function, you're supposed to call addref on that pointer. Whenever that pointer is not needed anymore, you're supposed to call decref, decrement reference count, in the end, using the pointer. Easy to forget. What about exception handling? You have to do somehow manually that create Python exceptions and convey errors back to your Python side of things. Very difficult. It's a lot of boilerplate that is needed to define the functions on the side, on the C function to bind that. And we will see some examples in a minute. Very high entry barrier because you have to understand how the C API on the Python side works, which is not trivial. In my experience, not too well documented. Well, it has vast documentation, but all the documentation tells you what happens when I call this function. No documentation tells you what do I need to do in order to achieve something. So you have to piece it together based on the API descriptions, what you actually have to do, and you have to look at examples and so on and so on. And last but not least, there are differences between Python versions. They have differences in the exposed API, and you would have to create several versions of your bindings just to go ahead or to be compatible with different Python versions. Let's have a look at a small Python example just to wean you off the idea to use that. As I said, Python is a compiler. It can compile Python and some extensions to Python that are built so you can build modules with them. For instance, a 2-line Python module can be transpiled to about 2,000 lines of C. 2 lines in Python, 2,000 lines in C. That tells you how verbose that C API is that Python exposes. So there's a lot of effort you have to do. It's a 2 build steps. So you first have to compile it to C, and then you compile your C to a shared library, which is always a bit difficult. Build system support is always one of the critical pieces in C and C++ development. It has very limited support for C++. You have to create stubs for anything outside the standard library. So if you have your own containers, you have to specifically write code for that by hand. So for a few functions, it's great, but for real projects, I wouldn't advise using it. So just to give you an example, these 3 lines of Python code, 4 lines of Python code compile to this mess. I don't want to debug that because it's impossible to read, okay? And you already see that is one of those functions that Python exposes. Pi error occurred, but that's the one. But that macro is probably from the Python API. Try debugging that. Try to kind of connecting that back to your original Python code. It's very difficult, so you have to invest a lot of time. I'll stop talking about these things at this point because I'm not a fan of it. Feel free to do it and play around with it. I wouldn't do it. Let's talk about PyBind 11. PyBind 11, as I said, is a very lightweight header-only library, so you don't have to compile a separate library. You just add an include statement to your own C++ code and you can use it. So it allows interacting with Python and with a Python interpreter, and you can write Python extensions with it easily. About 8,000 lines of code. It supports all Python versions, and the interesting thing is it directly supports NumPy. And I will show you in the end an example how to integrate NumPy with the C++ side of things, and how easy it is to work with NumPy data. Nowadays, NumPy is one of the basic infrastructure libraries used in AI and in scientific computing and so on. So NumPy support is very, very critical. You can embed your own Python interpreter on the C++ side. So you can write a C++ code that has no relation to Python itself because a Python interpreter is part of your C++ code. So you can do it the other way around, not just use PyBind 11 to write modules that are imported in a Python code, but you can use PyBind 11 to write your C++ code and use existing Python code and integrate it with your C++ side of things. Very nice. It supports STL data types, vectors, strings, all the containers. It supports overloaded functions, enumerations, callbacks, and so on and so on. So the whole gamma of C++ features you would like to have supported are supported. Just a link for you if you want to download it. There's a lot of documentation available as well. So it's designed for simplicity without sacrificing computing power. It helps creating Python bindings for existing C++ code in the following way. And just to give you a glimpse, I will most likely don't have that boilerplate on all the remaining slides. But this is a minimal Python module, which doesn't do anything. But you could do import example on the Python side. So what that does essentially is you import PyBind, you shorten the namespace to what people usually do, to Py, and I will use always the namespace Py : on all the slides. And then you say PyBind 11 module example M. What does it do? Well, this defines a Python module. The C++ name of this Python module is M. So it's an object that has a name M. And that Python module has a name example, so you can later import example into your Python side of things. That these braces are kind of a body of a function, and that function is called by Python whenever you load the module. So it contains all the initialization code for your Python bindings. Okay? Okay, so let's start with a simple thing and say, okay, I have a simple C function which adds 2 integers. Well, it's the simplest thing I could think of. So let's do that. I call the function add. And all I have to do in order to create a Python module that allows me to call that function is to say, my Python module, I call it the module myAdd. And then I say m.dev, m is that module, right? .dev, add is the name of the function on the Python side. The address of the function to bind, and some help text that can be used on the Python side to look at that extension. I could use a lambda in the same way, right? I don't have to use a function itself. I can just plop the function itself as a lambda into the module definition, which is usually what you do because it's usually small functions you want to just expose to the Python side. So these 2 things are completely equivalent. Okay, so let's import our module. From myAdd, import add. I'm importing that function. Help add works right away. It tells me that it's a function which takes 2 arguments which are integers and produces an integer. And it gives me the help text I specified, right? I said add 2 integers as a help text. So it gives me that help text right away. This automatically generated for you. You don't even have to generate that. And you get a very nice description on the Python side. You can modify the help text. You can even create extensive documentation from it. So Python uses usually Sphinx for generating documentation. PyBind11 supports that directly so that you can format your help text in a certain way and it will pass that on to Sphinx so you have a proper Sphinx documentation as well. Now let's add 2 numbers. Well, 1 plus 2 is 3. And when I try adding a string with another string, I get an error message which is quite descriptive, saying incompatible function arguments, the following argument types are supported and invoked with two arguments. So you get nice error messages as well from your bindings. And all of that with 3 lines of code. So it's great. Okay? So you already see where all of this is going. You write your C++ code, and with very simple kind of declarative way of declaring your bindings, you get full-fledged Python bindings without having to wade through all of that gibberish like Python is generating. And you can debug it easily. You just set a breakpoint on your C++ code when you run Python, and you can debug it. VS Code nowadays supports to run a Python debugger and GDB at the same time. So you can step through your Python code, and whenever you hit a function which is loaded in GDB, GDB will stop there, so you can go back and forth between the two. So it's a very nice development experience. You can debug these things in a nice way. Well, I said build system is always an issue. Not here. If you're using CMake, and I hope I convinced you over the semester that CMake is a good thing to use. It's not the best thing you could think of, but it's the best thing we have. So if you want to integrate and create a Python module, all you have to do, you do PyBind11, add module, myAdd, and specify the CPP files. Done. It will generate the build system for you. So after that, it will generate a shared library, which is called libmyadd.so on Linux or myadd.dll on Windows. And you can use that directly to load that into your Python environment. The only thing that is necessary, and that is kind of self-evident, you have to install the Python dev package. So the libraries and the header files that represent the C API on the Python side, which is a no-brainer nowadays. You just, on all operating systems, this is easily done. Okay, so what I want to do is I want to create a HTTP response class, a type that represents an HTTP response. And I want to start with the Python side of things to give you an idea how that would like in Python. a class response which has 3 members, status, reason, and text. It has a constructor where I can initialize my type, which is on the Python side, for those who never did Python, underscore, 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 underscore are those special functions you can write on your types to do certain things. And this is the equivalent to a C++ constructor with the arguments 200, OK, and text. What's called this in C++ is usually called self in Python. So I just stick to that convention. So all the constructor does, it initializes itself from its arguments. So all the members are initialized from its arguments. Just for the sake of it, I added an operator which allows me to compare 2 response instances. Again, with a special underscore underscore function name. Python allows you to do that. So whenever you compare 2 instances, Python will automatically call that operator for you, and whatever it returns will be used as a result of that comparison. And we define 2 instances to be equal as long as all 3 of the members are equal. You can do something else, but just for simplicity here. I add a representation implementation. The wrapper, whenever you call wrapper on a Python object, you get some extended description of that instance. And you implement that on your type by creating that underscore underscore wrapper function, which in this case just gives us the status and the reason, but you could do whatever you want there. And last but not least, just for the sake of it, I want to define a read-only property which is called OK, which I can use on my instances. So I can say response.ok, and it will give me yes or no, or true or false, depending on whether the status is in a certain range of HTTP responses. Nothing difficult. So keep that in mind, because this is what I will kind of port over to C++ over the next couple of slides. It has quite a gamma on different features we want to look at, so I will go through all these features one by one. Please ask questions if something is not quite clear, or so, if you want to have something explained. Okay, so what is the equivalent C++ code? Well, if I was to write that code, I would create a struct with these 3 members, integers, strings, and, well, 2 strings and an integer. I would add a constructor that allows me to specify the status and the reason, leaves off the text as being defaulted to nothing. Just for the sake of it, I added a default constructor which initializes the response object. Sorry, and that should be capitalized R here, to 200 and OK. And that OK function, which we will wrap into a Python property so that we can read it. Also, comparing 2 instances of response, we have seen that many times. All you have to do, you define a operator equal equal, which will be used by the C++ compiler whenever I compare 2 instances of that response type. Functionally equivalent, 100% equivalent to what I had before on the Python side. But now I want to be able to remove my Python implementation, which is in the file response.py, and want to replace it with a module which is a libresponse.so or something like that, which has my C++ implementation in it. And I can continue using my Python code that was using that response type without even touching it. Okay, so let's start. First of all, we have to expose the type to Python. The way you do that is you call a special helper, class underscore, where you specify the type you want to bind in as a template argument. You want to expose it from the module M, and response should be the name to be used on the Python side. You could add additional help text arguments here and other things, but I just leave it off for brevity. No surprises, really. And that's it. That exposes a response type to Python. You can't call any members yet, but the type will be already there. And you should be able to import that response module already. So once you compile that, you can do import response. And you can do from response import capitalized response, and that would work as well. You couldn't do anything with it because there's no functionality on it, but you could import it. So as I said, there's that pi : class. By the way, the underscore, why is there an underscore? Anybody? Yeah.
Because you can't use the class keyword.
Right. Otherwise, it would be a C++ class keyword. So they just postfix underscores to the function names and variable names that otherwise would be C++ keywords. We have the same with module and other things. So whenever you see that underscore, it's really just to avoid the clashes with keywords. Okay, let's expose the constructors. As you already might guess, it isn't too difficult. The only thing, well, the first one is easy, right? It's a default constructor. It doesn't take any arguments. That's why the template argument list is empty. In it is that predefined function in PyBind 11 that is used to bind constructors. And you just bind it by saying .dev, whatever, m.dev. I have exposed that one function on the C++ side with two functions here. I could have used default arguments, and I will show you how we can use default arguments in a minute. But for now, since one of the arguments is defaulted and I can call the constructor either with 2 or with three arguments, I just define two different constructors bindings for it. And you already see that PyBind 11 allows us to do function overloading on the C++ side of things. So I can use the same name and expose it to Python, and PyBind 11 will figure out which of the functions is actually being called. So that .dev is kind of the workhorse of defining functions on objects or global functions in PyBind 11. The 3 instance attributes called data members in C++, you can bind them easily, and here I want to bind them in a read-only way because there's probably no reason to change them afterwards. All you're interested in is looking at them. So what I do is dev read-only. Again, the first argument is a name to be used on the Python side. And I'm binding the variables, the members, just by taking the address of the corresponding member. Address, response status, response reason, response text. And here you already see that I'm not specifying any types. I just say status or reason or text. And PyBind 11 figures out what type it is that is actually bound and creates the appropriate binding code underneath. So it uses the integer type on the Python side or the string type on the Python side. The other thing we see is that I can easily bind C++ types Python has no knowledge about. So standard string is one of those types that is defined in the standard library. And PyBind 11 is transparently mapping the standard library types to the corresponding Python types. So this will be converted to a Python string whenever I'm accessing it on the C++ side. Dev read only is the same as .dev, just that it exposes only the bound entity in a way that doesn't allow me to write to it. The property, we said we wanted to not call response.ok parenthesis, but we want to say response.ok without the parenthesis. So call it as if it was a data member. And this is easily possible. And we have seen the code how you do that in Python side. In PyBind 11, you do it this way. You just say, OK, this is a read-only property. I call it OK. I bind the address of that function, and that's it. And that will make that whenever on the Python side somebody writes response.ok, this will be converted into a function call on the C++ side and will return whatever that function returns. So I can have computed properties in that situation as well, which is sometimes very interesting because some properties need computation, like here, right? You have a more complicated condition you want to expose, so you do it that way. kind of nice. Last but not least, the comparison operation of the two instances. And this is done, again, by using the very same name Python is using to expose these functionalities from its own types. So you can, on the Python side, I showed you can use this function name, and the Python interpreter will know, okay, I have to use this function whenever somebody compares two values. Here, you bind it as a normal function. You just say, okay, I'm defining a function __ equal, which will be exposed directly to the Python side, and I give it the arguments, and just call the C++ thing. The only thing you might want to do is to tell Python, hey, this is actually an operator. So there's some specific handling in the PyBind library that simplifies things. But you don't have to do that. This really simplifies the code and makes it a bit more faster. But this scheme, I don't know, Python has 20, 30, 40 of those special functions: equal, not equal, less than, greater than, plus, minus, multiply, divide. So all the operators are exposable through these special functions on the Python side. So when you write your own integer class, you probably want to implement all the arithmetic operations. And you implement them using these __ functions. And since this is so widely used, PyBind 11 allows you that special syntax where you just say PySelf equals PySelf, and it will generate the appropriate code that will present itself as a comparison operation for that type. And that works for all the operators. So you could say PySelf plus PySelf, and it will generate the code that is used whenever two instances are being added, or when two instances are being multiplied, or whatever. Okay, so it's a very straightforward way to expose these special operators that involve two of the instances on the Python side. This is kind of neat. Kudos to whoever has come up with that idea. It's really, really nice. And again, you don't see any complicated C++ Python, C++ template code. There's a lot of templates going on behind the scenes, but you don't see it. It's a beautiful interface provided to you to declaratively, almost declaratively, define your bindings. You don't write any code really for the bindings themselves. You just declare that this function is actually this, and that function is actually that. Last function is that wrapper function. As before, I'm just binding it using the special function name on the Python side, and on the C++ side, I'm just generating a string that represents that current instance, and that's it. Okay, so this is the whole binding. That's everything. Everything I went through over the last 5 or 10 slides is combined here, and this is a full Python module that exposes the C++ response type in a way that is fully compatible with the original Python module I showed you in the beginning. So you can throw away your Python code and use that generated module instead. And if you put it in the right place, you don't even have to touch your code that was using the response type in any way. It's still import response. End of story. Any questions so far? No? Good. It's easy enough. I don't think it's complicated. It's just you have to get used to reading that, right? Because it has a bit of strange way of doing things with that continuous ... and the semicolon only in the very end. But, well, once you have it done once or twice, you get used to that very quickly. Let's try it out. So from response, we import our response type. We construct an empty one, which implicitly in the interactive environment we'll call the REPL function, which is 200 OK, because we initialized it to 200 and OK. Response default constructed .OK, which is our property, will give us true, as expected. If we create one from a 404 error with no found, well, the reason will be no found. And ROK is false, as expected. So things seem to work. And this is exactly what you had before on the Python side, right? There is no difference. Well, last but not least, if I compare two instances, well, it will return false because Why does it return false? It should return true, actually. Yeah, that's wrong. It should return true, because that is default constructed, which makes the object which has 200 and OK built in. So it should return true, actually. Sorry for that. I will fix it on the slides. OK, so to summarize, there is that macro, which is called pybind11 module, which is the heart of the pybind's binding mechanism. It generates a function that is called when the module is being loaded by Python. So Python calls a special function whenever it loads a module, which is supposed to initialize a module. And that macro generates that function for you. And all that def syntax calls back into Python and makes Python aware of the structure of the object and generates a wrapper object that looks from the Python side as if it was a normal Python object with all those functions implemented. So you can use it as if it was a normal function object. Yeah, py_module underscore, again, the underscore thing, because module is a keyword in C++ nowadays. The method produces binding code, and the module type also exposes many other facilities. Some of them I showed, def read only, def property read only, and so on and so on. So there are many of those. Let's be a bit more sophisticated and say, I want to have named arguments. Python has named arguments. Why not do it? Well, you can do it easily just by adding pyarg name as an additional argument to my def function, which will expose a greet function with one argument that can be used as a named argument with name equals to something. So on the Python side, greet stranger, well, it will print hello stranger. And if I ask it what it is, it will give me the API, the interface. It says it takes one argument, which is a string. Well, see, we have a C++ string here, but it still knows that it's a Python string and doesn't return anything because the lambda is void. And the text is explicitly taken from the definition. Sometimes I want to have default arguments. Well, you can do that as well. The easiest way to do that is just, in this case, I have two arguments, name and times, and I just assign one to the pyarg and tell it, okay, if the times is not given, just use one as its argument. Straightforward. And that exposes the mechanics to the Python side of things, so I can directly use that. As here, so when I call it without the second argument, it just calls hello Jeeves, and if I tell it to greet Wooster twice, it will do that. Actually, I don't know why it's calling it twice. There should be a loop around that here. I forgot that loop. Why is nobody telling me that? Right? Times, I have to call that print statement twice here, or times. I will certainly fix that. Another example is, and that is one of the very nice features. What we have seen so far is how to expose C++ types to Python. But how do I expose Python types to C++? Here I'm calling a function that actually is being called using a Python list on the Python side. And I'm directly accessing that Python list as if it was a C++ type. I can iterate over it. I can say for auto item over list, and then I can check each of the instances of that list, whether it's actually a string. By saying, hey, is that an instance of a Python string? Yes, then increment my counter, otherwise don't, and return the number of strings in my list. So if I call that count strings function with some Python list which has 1, 2, 3 strings in it, then it will return 3. So I can directly use Python types from the C++ side of things. I can directly, without copying the list over, right? It's directly using the internal representation of the Python data type that lives on the Python side of things from the C++. And I will talk about data conversion and how these back and forth between Python and C++ can work in a minute, just as one example. You can do the same thing with a dictionary. So here we had a list. Now we pass in a dictionary, and we can iterate over the dictionary and access the key and the value by saying item first, item second. Please note that item first and item second will be Python objects, so a generic base class that has no type. So Pi.11 doesn't know what that type is. That's why I have to tell it, please convert that Python object into a Python string and then print it. And that will also raise an exception if that thing I'm passing is actually not convertible to a string. So it will invoke the Python runtime type checking at that point, the same way as if I was trying to convert something that can't be converted to a string in the Python code. So okay, so if I have a dictionary with 2 entries and I say print it, well, it will print that as we expected. And it doesn't matter what type's in here, as long as those are convertible to a string, it will work just fine. Very Pythonic. I like that because it really gives you the feel of the Python language on the C++ side. You don't have to write complicated code. You can think in the same way as you are thinking when you're writing Python code, which is one of the benefits of Python because it gives you that nice high-level syntax that allows you to express things in a very easy way. Okay, what about support for star args and star KW args? For those who don't know Python, Python has a way to refer to all arguments of a function by saying star args. It will give you a tuple of all arguments. Or if you want to refer to all keyword arguments a function was called with, you refer to it with star KW args, which will give you a dictionary of the name of the argument with the value of the argument in there. So again, these things are represented directly in Pi.11, so I can refer to Python args as pi args and KW args, and I can ask them for their size. I can iterate over them because that is a tuple, that is a dictionary in the same way as before, so I can investigate what's actually going on. As an example, I call my function with 3 arguments and 2 keyword arguments, so it will print 3 args, 2 keyword arguments, because all we do, we look at the size of these Python objects. How many elements do I have there? Neat. One of the last examples, function overloading. I already mentioned it. If I have a C++ function, we know that we can overload them as long as the arguments are different. These functions are distinct. So if I want to bind 2 functions f, both named f, just with the only difference that one takes an integer, the other one expects a float, I can do that by adding 2 definitions to my Python bindings. And if I call it with an integer, it will return int. If I call it with a double, it will return float. And if I call it with something else, I will get the appropriate error message, which is also listing the available argument over the different overloads I have available for that. So this problem can be solved as well. Very important, especially when you're a C++ developer. You often have these functions overloaded for different types, so you don't want to wrap these functions separately into distinct names, so just to bind them. Pi.11 can do that. Let's talk about what data types are supported for the bindings. As you already seen, essentially it supports all built-in data types of C++, integers, floats, doubles, and so on. It supports all Python types, lists, dictionaries, tuples, strings, floating point numbers, integer, everything Python has as built-in types you can use directly, and they will be mapped to the corresponding C++ type right away. On the other side, the STL data types like std string, vector, tuple, map, set are exposed to the corresponding types on the Python side as well. So a vector is mapped onto probably a list. A tuple on the C++ side is probably mapped onto a tuple on the Python side, and so on and so on. I mentioned the Python NumPy library compatibility of Pi.11, which is nice because it gives you efficient conversion from standard vector and standard array to to NumPy arrays. And that extends to SciPy, Matplotlib, Pandas, all the libraries that actually rely on NumPy as a data representation. You can directly expose and use on the C++ interface as well. Here comes the interesting part. There are 3 ways to communicate objects between C++ and Python. You can work with a native type in the C++ world and work with a wrapper in the Python world for one thing. And that's what we've done with a response type. We have a native C++ type and we create a Python wrapper which exposes that C++ type to the Python side as if it was a Python object. That means that the type must be wrapped, and that's what I explained with a response type, and it will generate the necessary wrapper bindings that allow for the Python side to directly interact with a response type on the C++ side. Note that in this case, no data copying is happening. So whenever I have a response type on the C++ side and I refer to it from Python, the response type itself is never copied over to the Python side. I can use wrappers in the C++ and native in Python. I showed you that example when the py list, py dictionary, py string come into the bindings. Those are Python types, and C++ can directly refer to the things over on the other end of the pond. So those types pylist, pydict are essentially wrappers themselves that pretend that the Python things are actually C++ objects. So it's the opposite of the first. Last but not least, you can use native types on the C++ side together with native types in Python. This one is very convenient but a bit dangerous because it always requires copying of data. Right? When you pass a std string over to Python, then it will not be wrapped. It will be creating a Python string and copy the string over into the Python side of things. Same in the other direction. So when you use native bindings, you always copy data. For small things, it's probably the most convenient thing, right? For integers, for doubles, you don't need wrappers for that. You just copy the integer over and you're done. But for larger data types, especially NumPy or std vector or so, this can be performance critical. So be aware of that. But it's the most convenient way of doing things because you don't have to do anything. You just specify that type and it will be converted to something that is compatible on the other end. So let's go through these 3 a bit more detail. Native in C++, wrapper in Python. So you expose your C++ type using the py class underscore facility, like I showed. The underlying data structure is always the original C++ class. The py class wrapper provides a Python interface. When an object like this is sent from C++ to Python, py-11 will just add a wrapper and give the wrapper to Python. And when such a class comes from Python to C++, it just strips off the wrapper and gives you the underlying native object that is wrapped from the Python side. So it's a straightforward way to do things, and we have seen it with a response type that this works very well. If you have a wrapper in C++ and native in Python, this is cool because we have an interface that is based on the py object, which is the base class of all Python types. You might know that if you have written Python extensions, all Python types are derived from py object, all of them. Integers, doubles, strings, everything is derived from the py object base type. But py-11 gives you strings, bytes, tuples, lists, dictionary slices, none. Everything Python gives you has an equivalent Python, C++ object that wraps that Python object such that you can directly use it. So, for instance, I could write Python code in C++ by saying, OK, create a Python dictionary and initialize it from two elements, spam none and string x42. This creates a Python object on the Python side of things. So no C++ allocations are happening. It's all happening in the Python interpreter. Same with a tuple. Just make a tuple out of these 3 things. It does what it's supposed to do. You can cast things explicitly. You can say, OK, I have a C++ class, and I want to turn that into a Python object. Well, you just say, okay, please cast that into a Python object. The other way around, you can cast objects into the C++ type, which gives you a pointer to whatever is wrapped on the Python side. So you can go back and forth easily using these two facilities. The native one is, as I said, the most convenient one, but requires a bit more attention because it might involve copying a large amount of data across a boundary. So here I'm exposing a lambda that expects a vector and prints the elements in that vector. And on the Python side, I call that with a list. And it will automatically convert, see, okay, this is a one-dimensional sequential container, so the best thing to do that, and the C++ side expects a vector, these are compatible, so let's copy all elements from the list over into that vector and create a new vector instance and create that and call that function. So it will create a new vector int and copy all elements from the Python list into the vector. The same applies for return types. So when you return a standard vector, you will get a list on the Python side if you don't do anything special about it. Just a list of what's actually supported, and that's not a complete list, just for your reference, so you know if you ever want to know, hey, can I actually expose a std function to Python? Yeah, you can. Can I expose a std array to Python? Yeah, sure, you can do that. So let's not go through that for the sake of it, for the sake of time. A couple of links when you're interested in reading more. A bit more, kind of a kind of laundry list of things that are also available. I will not go into detail, so please read about it a bit more if you're interested. I talked about reference counting. I said, okay, Python object need to be reference counted. But you as seasoned C++ programmers will immediately say, oh, reference counting, cool, constructors, destructors. So what PyHandle actually does, no, the Py object, I believe, is when you construct a Py object from a pointer, it will, in the constructor, call the addref, and in its destructor will call the decrement reference count. So you don't have to worry about reference counting at all because the C++ compiler does that for you. And all the Python objects, PyString, PyList, PyDictionary, and so on, do that automatically because they are derived from PyObject. If you ever want to avoid reference counting, just use PyHandle, which is just a plain wrapper around the pointer without doing that reference counting. Just an example. I mean, engage with the USS Enterprise. Okay, so I have a tuple, which is a ship. I have two arguments, the bridge and the others. Jim and Spock and Scotty, and then I say engage. Bam. I can call that function right away. And as you see, I can use the star and the star syntax to explode tuples in the same way as I would explode them when I'm calling a Python function with a tuple and I want to separate the arguments while calling the function. Same works on the C++ side. I can import SciPy. Hey, let's import SciPy and call a function from SciPy. Just like that. So you say, okay, please import that thing which exists somewhere in the Python world and then call a function on that thing. So you can integrate arbitrary Python code into your C++ side easily by doing that. You can use PyPrint, PyFormat, so all these facilities are there. And you feel at home when you start using those because there's nothing missing, right? Whatever you would like to do in Python, you can directly, essentially, without even thinking about it, writing in C++ as well. Because the names are the same, the semantics are the same, and so on. Did you ever want to invoke Python code from C++? Sure. Here we go, some Python code, and I call pyexec, bam, it will run that. The only thing I have to do, I have to especially create an interpreter, a Python interpreter, which actually runs that stuff. That's it. So arbitrary Python code, call it in C++. You're too lazy to rewrite that nice facility you have there for years on your hard disk, but you want to use it in C++. Here you go. By the way, there's eval file as well, so you don't even have to copy the stuff over. You can read a Python file and can run it directly from the C++ side. Just to tickle your brain a bit, I thought, what can I do to stretch your imagination, to actually make you think about and wake you up from my longish explanations? What I want to do is to create some higher order functions. Anybody knows what a decorator is in Python? Decorators are these things with an ampersand you put in front of a function which creates a wrapper and uses that function as an argument to that wrapper function. So this is higher order functions, and I want to give you some examples for that. But let's start with calling Python functions from C++. So I have an extension function for even, which gets in an integer number of elements, and a Python function which I pass in when I call that thing. And what it does, it counts how many even numbers are between 0 and n, and calls my Python function for each of the even numbers. So if I have a callback which just prints whatever it gets, I can pass that callback to my C++ side of things, and that fi will invoke that Python function for us while iterating over it. As you see, it prints the even numbers. The only thing to remember is, or might be unusual, is that std function type. We had that in some of the lectures before, which represents a unspecified function where all we know is the prototype. It has to be a function that doesn't return anything and expects one argument of an integer. So it's a bit weird syntax, but just read it as a function prototype. So it can bind or can invoke any function that exposes that interface. And since our callback exposes that interface, right, it expects one argument and doesn't return anything, I can bind it to this std function easily, and PyBind 11 does that. Now let's do some higher order function. Let's say I want to write a function, I don't know, call it h, which takes two arguments, n, x and n. And what it wants to do is to multiply x with 2 to the power of n. So it doubles x n times. X times 2 to the power of n. Doubling x n times, okay? So I could write a simple function which does that, but why do the simple thing if we can complicate it a bit? Why not write a function which returns the function we are interested in? So apply n takes the function arbitrary function I want to invoke, the number of times I want to invoke that function. We had that in the first lectures. I talked about this kind of thing to death, right? Calling the function on itself over and over again and taking the result and use it as a new one, which is essentially that, right? I want to double the thing more than once. Each of those invocations doubles x. And then I apply n to the Python side. And please note the syntax. Let's talk about that a bit. It takes a function and an integer and returns a lambda which has a function and the integer bound, and takes one argument and uses that argument to apply the given function n times. Okay? So now we can say, okay, I have a function which doubles things once, and I'm applying that function 8 times, which gives me another function, and then I tell it call that other function for x equals 10, which gives me, well, 2560, hopefully. By the way, if you have heard of that, this method is called currying, when you have a function h, x, n, you convert it into two functions, g of x, which gives you another function which you can invoke with another argument. So you pre-bind one of the arguments to a function and then use that pre-bound argument with a second argument and get the same result as before. This is exactly what's happening here, right? I'm pre-binding my n and then that 8, and then I use that 8 inside g to actually execute that thing 8 times. Okay? So it's not complicated. It's just making things more weird. But as I said, just to wake you up, to get you thinking about these things. So we have a higher order function. Higher order function is a function that returns or takes a function as arguments. Why not wrap that even more? Let's create an even higher order function, which takes our bound function, well, which is that thing, same as before, but this time it binds it again, but binds the other argument, binds the function, right? This binds both, and this one binds only n and invokes it with a function to invoke. So it's splitting that thing, kind of wrap that thing again, which makes it a Python decorator, by the way. Okay, so we bind it, and if you look at that code now, we can call the first apply function as before with f and 8 and 10, but we can also say, well, I have another function g which actually doubles things. I apply that other function as a decorator, which automatically wraps that thing, and then I invoke g on 10 and will get my result. So you can do very nice function composition when you think about that. Well, in this case, it's probably useless, but if you ever want to do currying and you want to develop a decorator, and that's what I'm aiming at, you can easily implement decorators using PyBind 11 on the C++ side, which wraps the Python function, does things, calls the function, does other things, essentially, which is a very convenient way and widely used in different Python libraries in various ways. Okay, last but not least, let's look at a Python NumPy example. Just to convince you that it actually is beneficial to do that. What I want to do, I want to implement a function which calculates the rolling statistics for a given array, where the statistics computed are the mean and the standard. It will compute the standard and the mean. So what does this code do? And I will not go through all the details, but just the important things. It receives a pi array double, which means it's a NumPy array of doubles. It specifies an additional argument, how wide the rolling window should be when I go over that array to compute the mean and the standard. Then I declare a new pi array, which is a NumPy array, of a new type, stats, which is that type. So I can even declare my own types to be wrapped in NumPy. And all I have to do, I have to say, okay, there's a new NumPy D type, which is stats, and it has these two members. Please bind them in a way so that I can use it as an element in a NumPy array. And for those who have worked with NumPy, you know that you can store arbitrary things in NumPy, but you have to tell Python and NumPy about these things. So this one line does that. It creates it wraps stats in a way so that you can use it as an element in a NumPy array. So I can create a new NumPy array of those stats. Well, then there's a loop of doing things, it computes things, and in the end it returns that array of that NumPy array. The good thing about that scheme here is that the NumPy array lives on the Python side, and the C++ code only uses pointers to refer to the data that is actually stored on the other side. So you can do that with very, very large NumPy arrays without having to be afraid that you're actually copying things over. So you're just handing the pointer to the NumPy array to the C++ side, and there it uses the NumPy API to operate on that native NumPy data structure. Well, it's just doing a bit of statistics, calculating things. It's not that important and not that interesting. But what I want to show you is the following. I import Pandas. I initialize my data frame using my rolling stats function, which I initialize from a Python list, which has 5 elements. I say, okay, window is 2, not too important. And Pandas will give me that table, right? Pandas does that for you. So I really pass in just a Python list, but get back a NumPy array from my rolling stats, which data frame can handle properly because it's a NumPy array, and data frame relies on NumPy arrays. So it works. It gives you exactly what you want. So let's do a correctness check. Let's compare that with calling the rolling functionality on the Pandas side. right? I can do the same thing I implemented using Pandas by just saying rolling.mean, rolling.standard, which does exactly the same computation as I implemented on the C++ side. Just to show you when you run this code, these assertions will not fire. So it produces a correct result. This is what I'm aiming at. But the more interesting thing is, when I do some measurements, how long does it take to compute these things? So I have a 25 million NumPy array. I'm passing that 25 million NumPy array to Pandas and get a rolling object, which I can use to compute these statistics. And when I call rolling mean, well, it takes about a second to do that. Not bad. I call rolling standard, it takes about same amount of time, roughly, to compute the standard deviation for these 25 million elements. And now I do the same with my function, which computes both. And it takes 250 milliseconds. So it's essentially 10 times faster than what the Python side can do and what Pandas does. And you would think that Pandas is highly optimized and NumPy is highly optimized because millions of people use that. And Pandas has been optimized to death, believe me. They have invested a lot of time into doing that. But just by writing 100 lines, not even 20 lines of code, you can speed up your computation. Well, not quite a factor of 10, but what is it? Well, let's say 4, roughly, to do the same computation. Isn't that great? So that's where the combination of C++ and Python comes from. You have the ease of use you are used to from Python, but you have the performance you're used to from C++. Just by investing a bit of time and taking the time to implement certain things, the performance critical things yourself. Not everything, but only the things you're interested in. Okay, any questions so far? I'm not going to talk about that. That's boring. There are many other things for your reference that Py.11 does. One of the critical things is you might know that Python has a so-called global interpreter lock, which is a mutex that is acquired whenever Python code is running, which makes it a pain to integrate threading libraries like HPX with Python, because whenever you call into Python, you have to acquire that lock. And whenever you come out of Python, you have to release that lock so you can do your C++ side of things. But Py.11 gives you at least facilities that allow you to easily handle the global interpreter lock. Newer versions of Python, I believe version 3.14, if I remember correctly, have an option to get rid of the global interpreter lock. So if you want to do parallel computing with Python, I'd suggest that you use a newer Python version that actually has no global interpreter lock anymore, because that is a pain to manage and slows down things. Well, just imagine you have 64 threads working on the C++ side and constantly have to call on the Python side to get data. On each of those calls, they have to acquire a single mutex that protects the data, the Python engine. So you don't need 64 threads to make that thing slow, right? 2 threads already might, or 4 threads already might create that mutex into the absolute bottleneck for your computation. So I'm just listing it here for your reference in case you're interested, so you know that there's much more. There's even more than I even listed, but the gist is, and I'll shut up on that one, you can combine the good things of both worlds without gaining the bad things of both worlds. And that is the important part. And that's why Python and C++ are beautifully aligned and can be easily combined using these kind of technologies. Okay, so that's it from me. Thank you for being here. It was fun for me to do these lectures. If you have any questions or anything, please get in contact. And I hope to hear a lot of nice presentations the week after next. Thank you so much.